On May 31st, 2026, Microsoft and NVIDIA announced a Windows PC platform that would have sounded almost impossible a decade earlier. RTX Spark paired NVIDIA Blackwell graphics with a high-performance CPU built on the ARM architecture and up to 128 gigabytes of unified memory. Microsoft said the chips would power new Windows laptops and compact desktops from Surface, Asus, Dell, HP, Lenovo, and MSI beginning that fall. But buried inside the announcement was the detail that revealed the real state of Windows on ARM. Microsoft was still tuning Prism, its x86 and x64 emulator, specifically for the new processor so decades of old Windows software could survive the transition. The operating system had already been ported. The problem was everything Windows had accumulated around it: applications, drivers, plugins, anti-cheat systems, installers, virtualization tools, corporate agents, obscure libraries, hardware utilities. Every one of them represented a piece of the x86 world that could refuse to cross the architectural boundary. At the same time, Qualcomm's second-generation Snapdragon X2 chips were moving beyond thin laptops and into mini PCs and desktop designs. ARM was no longer approaching Windows from the edge of the PC market. It was moving toward the center of the machine. And Microsoft faced a contradiction that Apple had largely avoided. To make ARM succeed, Windows had to become less dependent on x86. But to remain Windows, Microsoft had to keep almost everything built for x86 working. That is why the current ARM race is not really proving that Microsoft cannot port Windows. It is proving that porting Windows is the easiest part. The harder task is porting 40 years of expectations without allowing users to notice that anything changed. That distinction becomes visible the moment a user leaves the safe path of mainstream applications and touches the deeper machinery of Windows. A normal x64 program can often survive through Prism, but a kernel driver cannot. Microsoft requires those drivers to be rebuilt for ARM64. That single boundary can decide whether a security tool, audio interface, virtualization package, old printer, or anti-cheat system works at all. And it explains why increasingly powerful ARM PCs can still expose compatibility failures that have nothing to do with raw processor performance. The silicon may be ready, Windows may be ready, the application itself may even run. One forgotten dependency can still stop the entire workflow. That is the trap Microsoft created by making backward compatibility one of Windows' defining advantages for more than 3 decades. Every preserved interface made Windows more valuable, but every preserved assumption also attached another piece of software history to the x86 architecture. Now ARM processors are improving quickly enough that those assumptions are being tested not just in thin laptops, but in creator machines and desktops. The faster the hardware advances, the less acceptable it becomes for users to discover that an old driver or plugin is the real performance ceiling. Microsoft is no longer proving it can make Windows run on ARM. It is proving whether Windows can remain Windows after x86 stops being mandatory. Microsoft has been here before, and the first attempt ended very differently. When Windows RT arrived with the original Surface in 2012, Microsoft had an ARM version of Windows, but the software world around it was brutally constrained. Traditional desktop applications compiled for x86 processors did not simply work. The machine looked like Windows, but one of the deepest promises of Windows, the ability to install familiar desktop software, had been broken. The failure exposed a lesson that would shape every later attempt. An operating system is not just a kernel, scheduler, graphics stack, and user interface. A desktop platform is an agreement between the operating system and millions of programs written across different eras. If the processor architecture changes underneath that agreement, software compiled for the old instruction set cannot automatically execute on the new one. x86 and ARM solve the same general computing problem with different instruction set architectures. A program compiled into x86-64 machine instructions expects a processor that understands those instructions and the conventions surrounding them. An ARM64 processor speaks a different machine language. Source code can often be recompiled, but a finished binary cannot simply be wished into native ARM code. That is why emulation became Microsoft's bridge. Windows 10 on ARM allowed many unmodified 32-bit x86 applications to run through translation. Windows 11 expanded compatibility to unmodified x64 applications. Then, Windows 11 version 24.8.2 introduced Prism, a newer emulator designed to improve performance and reduce the CPU cost of translating software built for x86 into instructions an ARM processor can execute. The achievement is easy to underestimate. When an old Windows application launches on a modern Snapdragon machine, the user may see the same menus and files and assume nothing unusual is happening. Underneath, Windows may be translating blocks of x86 code, mapping system calls into native operating system components, preserving memory semantics, handling exceptions, and making the foreign application believe it is still living on the architecture for which it was compiled. But translation has limits. Microsoft itself tells developers that native ARM64 applications deliver the best performance, responsiveness, and battery life, because emulation carries overhead. The faster ARM hardware becomes, the more awkward that overhead looks. A machine can possess an extremely efficient processor, while an old application burns additional cycles translating instructions the chip was never designed to execute directly. Microsoft created ARM64EC partly to escape that all-or-nothing trap. The technology lets developers rebuild portions of an existing Windows application as ARM-native code, while leaving other x64 components running under emulation inside the same process. A massive application with years of dependencies can migrate piece by piece instead of waiting for every library and plugin to become ARM-ready at the same moment. That design reveals the real obstacle. Windows applications are rarely isolated executables. A creative program may load codecs, GPU libraries, audio plugins, scripting engines, printer components, licensing services, capture drivers, and third-party extensions. An enterprise application may depend on authentication middleware written years ago. A developer tool may invoke command line utilities compiled by entirely different projects. One missing ARM dependency can block the supposedly simple act of recompiling the main application. And then, the compatibility bridge reaches a wall. Kernel drivers cannot be emulated. Microsoft requires kernel mode drivers on ARM systems to be built natively for ARM64. A legacy x86 or x64 driver cannot simply pass through Prism and gain permission to operate inside the ARM kernel. This is one of the most important boundaries in the entire transition, because drivers are where software reaches deeply into hardware and the operating system. That includes more than printers. Security software can depend on low-level drivers. Virtualization products may install them, specialized audio equipment may require them, hardware monitoring tools, storage utilities, industrial devices, VPN products, accessibility hardware, and gaming anti-cheat systems can all cross into privileged territory. A normal application can often survive through emulation. A missing driver can make the entire product unusable. This is why Windows on ARM has repeatedly improved in strange-looking steps. One year, a browser finally becomes native. Another year, a VPN vendor appears. Then, a game starts working because its anti-cheat provider added ARM support. Then, a graphics application gains a native build, but one popular plugin remains x64. The platform moves forward not as one clean migration, but as thousands of independent dependencies finally lining up. By 2024, Microsoft had reached a turning point with the Snapdragon X Elite and X Plus generation. The company launched its first wave of Copilot Plus PCs around Qualcomm's ARM processors and promoted long battery life, high performance, and dedicated neural processing. Microsoft also said nearly 90% of the time users spent inside applications on those machines could already occur in native ARM software. Chrome, Microsoft 365, Zoom, Slack, Spotify, and major Adobe applications joined a growing list of native software. That changed the everyday experience dramatically. Earlier Windows on ARM machines could feel like compatibility experiments. A modern user who lived mostly in a browser, office, messaging applications, streaming tools, and mainstream creative software could spend much of the day without thinking about architecture at all. But the remaining 10% could matter more than the first 90%. A professional does not judge a workstation only by how long the most common apps remain open. One missing corporate security agent can block deployment. One unavailable audio driver can kill a studio workflow. One anti-cheat system can decide whether a game launches. One native plug-in dependency can determine whether a production pipeline survives. Apple faced the same binary translation problem when it announced the Mac transition from Intel processors to Apple Silicon in June 2020. But Apple controlled conditions Microsoft could never fully reproduce. It designed the processor, operating system, development environment, hardware lineup, and much of the software distribution model. It gave developers universal binaries that could package Intel and ARM code together, and Rosetta 2 allowed many unconverted Intel applications to run during the transition. Apple also announced a roughly 2-year transition. It could eventually stop selling Intel Macs and push the entire active Mac hardware lineup onto its own ARM-based silicon. Developers who wanted access to new Macs therefore received an unavoidable signal. Native ARM support was not an optional experiment. The platform itself was moving. Microsoft cannot issue the same ultimatum without risking the reason many customers use Windows. Intel and AMD PCs remain enormous parts of the ecosystem. Businesses have expensive x86 fleets with long replacement cycles. Game developers target a market filled with x86 processors. Peripheral vendors may support hardware for a decade. Corporate software can remain in production long after the team that created it has disappeared. Windows, therefore, has to support architectural pluralism. Microsoft is not moving the entire PC market from one instruction set to another on a fixed 2-year schedule. It is trying to make Windows equally believable on x86, 64, and ARM64. while allowing users to carry software across the divide. That is a harder platform problem because the old architecture does not go away and force developers to move. The success of x86 emulation can actually slow native migration. If an application works well enough through Prism, a developer may decide that rebuilding dependencies, testing installers, fixing architecture-specific code, and maintaining another release target is not yet worth the engineering cost. Compatibility protects users, but it also removes urgency from developers. Microsoft tries to counter that by improving the economics of native software. Visual Studio runs natively on ARM. .NET supports ARM64. GitHub has added ARM-oriented build infrastructure. Microsoft provides an ARM advisory service to help developers port applications and drivers. ARM itself launched App Ready for Windows in 2026 to centralize migration guidance, dependency checks, compiler advice, and engineering support. The existence of those programs is not evidence that Windows on ARM is failing. It is evidence that the ecosystem is now large enough for migration friction to become strategic. ARM's Windows software dashboard listed hundreds of supported packages by 2026, including development tools, media frameworks, networking software, AI libraries, and applications that had only recently gained native Windows on ARM versions. The dates tell their own story. Visual Studio became native years after Microsoft's first modern ARM PCs. GitHub Desktop did not gain official Windows on ARM support until late 2025. GStreamer added support in 2026. VLC's native Windows on ARM path matured in the same period. Each arrival closes a gap, but each gap also proves how long software architecture can outlive hardware architecture. Then the silicon accelerated again. Qualcomm announced Snapdragon X2's Elite and X2 Elite Extreme with up to 18 CPU cores and NPUs capable of roughly 80 trillion operations per second. In 2026, those processors appeared across new premium laptops, and Qualcomm expanded the Snapdragon X family toward desktop and mini PC designs. ARM was no longer being sold merely as the architecture that saves battery in a thin travel machine. That expansion changes developer incentives. A program compiled only for x86 can survive on an ARM laptop through emulation, but the cost becomes more visible when ARM machines compete for demanding workflows. Creators want maximum GPU throughput. Developers want fast compilation. Local AI workloads want memory bandwidth and efficient access to accelerators. Gamers want low latency. Every translated layer becomes another reason to produce a native build. NVIDIA's RTX Spark announcement made that pressure impossible to dismiss. The platform combines Blackwell-class graphics with an ARM-based Grace CPU design and unified memory, aimed directly at creators, AI developers, and gamers. Microsoft said Prism would be present and specifically optimized for the new hardware, including improvements that built on recent support for AVX and AVX2 instructions used by many x86 applications and games. AVX support illustrates how deep the compatibility problem goes. x86 software is not just a sequence of generic arithmetic instructions. Modern applications can depend on specialized vector extensions developed across generations of Intel and AMD processors. If a game, scientific package, media encoder, or plugin expects AVX2, the emulator must reproduce enough of that behavior efficiently for the software to remain useful. The architecture transition therefore becomes a moving target. Microsoft is not translating one frozen version of x86. Developers keep using new libraries, instruction extensions, graphics APIs, security techniques, and hardware assumptions. At the same time, ARM processors add their own capabilities. The bridge must evolve from both sides while preserving decades of Windows behavior. Gaming exposes the tension more clearly than almost any other category. Raw CPU speed is only one requirement. Games depend on graphics drivers, launchers, anti-cheat systems, middleware, overlays, controller software, shader compilers, and sometimes instruction set assumptions buried deep inside engines. A title can perform well under emulation and still fail because one security component refuses to load. By late 2025 and 2026, that situation was improving. Qualcomm promoted downloadable graphics driver updates, expanded AVX and AVX2 emulation, and better anti-cheat compatibility. Microsoft's 2026 RTX Spark announcement pointed to easy anti-cheat and BattleEye support and said major titles, including League of Legends, Valorant, and PUBG, were moving toward the platform. Progress was no longer theoretical, but the work required to reach basic equivalence exposed how much infrastructure surrounds a Windows game. Creative software tells a similar story with different dependencies. By 2026, Microsoft listed Blender, DaVinci Resolve, Cinema 4D, Redshift, CapCut, Cubase, Bitwig Studio, Affinity, Photoshop, and Premiere among applications with native ARM support or dedicated optimization around RTX Spark. That is a far stronger creator ecosystem than Windows on ARM possessed only a few years earlier. But professional workflows extend beyond the headline application. A video editor can depend on capture hardware. A musician may own an audio interface whose vendor has not released an ARM driver. A 3D artist may require a proprietary renderer or asset management plugin. A photographer can depend on tethering software built around an old device SDK. Microsoft cannot port those components because Microsoft does not own them. This is the part of the story hidden by the phrase port Windows. Windows itself contains extensive ARM native code. Microsoft has native versions of core applications and development tools. The company has built an emulator sophisticated enough to make enormous amounts of unmodified x86 and x64 software run transparently. The bottleneck is distributed across thousands of independent vendors whose priorities are not controlled from Redmond. That makes the ARM transition a coordination problem rather than a compiler problem. Microsoft must create enough compelling hardware demand that developers care about native ARM performance. Hardware vendors must ship enough machines to justify that investment. Developers must port enough software that customers trust the hardware. Customers must buy enough machines that OEMs keep building them. Every part of the loop depends on the others. Apple escaped much of that loop by controlling a vertically integrated market and removing the old hardware from future product lines. Microsoft has to generate momentum while continuing to support the architecture. ARM is challenging. Intel and AMD are not standing still either. Both are improving performance per watt, integrating stronger NPUs, and producing processors designed for the same thin, AI-focused Windows machines Qualcomm wants to own. So the rise of ARM does not automatically mean x86 is dying. It means processor architecture has become competitive again inside mainstream personal computing. For decades, a Windows PC was almost synonymous with an x86 compatible processor. Now Microsoft increasingly designs Windows features, developer tooling, application frameworks, and compatibility systems around the assumption that the hardware underneath may come from fundamentally different instruction set families. That shift has consequences inside Windows engineering. Code that accidentally assumes x64 must be isolated. Build systems need ARM targets. Installers need architecture awareness. Windows libraries must be available in native forms. Testing matrices expand. Performance teams must distinguish native bottlenecks from emulator bottlenecks. Security engineers must ensure compatibility layers do not weaken process boundaries or code integrity. It also changes what native means for a Windows application. ARM64EC allows a single process to combine ARM native components with emulated x64 pieces. ARM64X binaries can contain code designed to serve multiple architecture contexts. Microsoft is effectively building a spectrum between pure x64 and pure ARM64 rather than demanding one irreversible jump. That is an engineering advantage because it lets enormous programs migrate gradually. It is also evidence of how deeply x86 conventions are embedded in Windows software. The new architecture is being designed to coexist with the old one inside the same application process because forcing a clean break would strand too much valuable code. The pressure increases as ARM hardware becomes more specialized. Modern ARM systems are not simply replacement CPUs plugged into traditional PC motherboards. They are increasingly systems on a chip integrating CPU cores, GPU blocks, neural processors, security engines, memory controllers, media accelerators, connectivity, and power management logic. The operating system has to understand the entire platform to extract its efficiency. This is one reason battery life became the original Windows on ARM selling point. An integrated SoC can move workloads between specialized blocks instead of waking a large general-purpose CPU for everything. Video decode can run on dedicated hardware. AI inference can move to an NPU. Background sensing can use lower power components. The advantage appears only when software is written to use those paths. Emulation can preserve compatibility, but it cannot automatically redesign an old x86 application's architecture around an NPU or a specialized accelerator. The application may run, yet leave some of the most valuable silicon idle. Native migration therefore becomes more than instruction translation. Developers have to rethink where workloads execute if they want the full performance per watt advantage ARM vendors are selling. The AI PC era magnifies that difference. Microsoft established Copilot Plus requirements around capable NPUs. And the first Copilot Plus wave arrived on Snapdragon X systems before Intel and AMD versions followed. Qualcomm then increased NPU capability in its X2 generation. NVIDIA's ARM-based RTX Spark pushed the idea further by combining an ARM CPU with extremely powerful graphics and unified memory for local agent and creative workloads. Unified memory is another challenge to old assumptions. Traditional Windows applications evolved around systems where CPU memory and discrete GPU memory could be separate pools, requiring copies and explicit management. New integrated designs can offer large shared memory spaces across compute engines. Microsoft said it was changing Windows memory management behavior for RTX Spark to support larger pages in shared memory regions and help demanding workloads exploit the architecture. That is not merely Windows being ported, again. It is Windows being adapted to a different model of what a PC looks like. The platform has to preserve Win32 compatibility while becoming comfortable with SoCs, unified memory NPUs, ARM cores, mobile-style efficiency, and heterogeneous compute. The old desktop contract is being stretched over hardware that increasingly resembles the integrated designs that transformed smartphones. There is still a reason Microsoft refuses to break that contract. Windows became dominant partly because businesses could replace a machine without replacing every workflow attached to it. An accountant could keep an old plugin, a factory could keep a device control program, a gamer could install a library from a decade ago, a developer could run obscure command line tools. Compatibility became a form of accumulated economic value. ARM turns that value into technical debt. Every compatibility promise creates another behavior that must survive translation. A cleaner operating system could simply declare old binaries unsupported and force developers forward. Windows cannot do that casually because the mess is also the product. The result is a race in which Microsoft is simultaneously accelerating and applying the brakes. It wants native ARM software because native code unlocks efficiency. It wants Prism to become nearly invisible because users refuse incompatibility. The better Prism gets, the less pressure some developers feel to port. The slower developers port, the more important Prism becomes. This explains why a mature Windows on ARM machine in 2026 can feel both finished and unfinished. Open a browser, Office, Slack, Photoshop, or native development tools, and the architecture may disappear completely. Install the specialized peripheral, an old game, a corporate endpoint agent, or a niche plugin, and suddenly the processor architecture becomes the most important fact about the machine. Those edge cases are shrinking, but Windows is defined by edge cases at extraordinary scale. Microsoft does not need ARM to run 95% of software. For many customers, it needs the exact remaining 5% they depend on. That last fraction can take longer to migrate than the entire mainstream ecosystem because it contains software with small user bases, old code, missing maintainers, hardware dependencies, or little commercial incentive. The emergence of multiple serious ARM PC vendors could finally change that calculation. Qualcomm established a broad Windows laptop portfolio. NVIDIA entered with RTX Spark for high-end creators and AI workloads. ARM itself began investing more directly in Windows developer migration. As more OEMs ship ARM systems across price points and form factors, ignoring ARM becomes harder for software companies. That is the real meaning of 2026. The Windows on ARM question is no longer whether Microsoft can make the operating system boot on an ARM laptop. That problem was solved years ago. The question is whether ARM becomes economically important enough that the entire Windows ecosystem treats ARM64 as a first-class target rather than a compatibility mode. If it does, Microsoft wins even while x86 loses exclusivity. Windows does not make money by defending one instruction set. Its strategic value comes from remaining the software platform customers choose regardless of the silicon underneath. A Windows ecosystem that runs equally well on Qualcomm, NVIDIA, Intel, and AMD would make Microsoft less dependent on any single processor architecture. But reaching that position requires Microsoft to move faster than the fragmentation it created over decades can slow it down. Every new ARM device raises expectations. Users compare battery life with MacBooks, application compatibility with x86 Windows PCs, gaming with conventional gaming laptops, and AI performance with whatever new accelerator arrives next. It works under emulation becomes less impressive as native competitors become faster. The irony is that Microsoft is now solving a problem created by one of Windows' greatest historical strengths. Backward compatibility allowed the ecosystem to grow enormous. That enormous ecosystem made Windows difficult to leave. Now, the same ecosystem makes architecture migration unusually difficult because millions of binaries assume that the processor underneath them belongs to the x86 family. Apple demonstrated that a company can move a desktop platform to ARM quickly when it controls the hardware transition and can eventually close the old road behind it. Microsoft is demonstrating something harder, how to open a new road without closing the old one, while letting applications move between them at different speeds. Prism is the traffic system, ARM64EC is the temporary interchange, native ARM applications are the destination, drivers are the checkpoints where translation stops, and every new Snapdragon or RTX Spark machine adds another lane before all the old vehicles have been rebuilt for it. The race is therefore not Microsoft versus ARM. Microsoft has already embraced ARM deeply enough to make Surface systems, development tools, emulation technology, and Windows itself depend on its success. The race is between the speed of ARM hardware innovation and the speed at which the Windows software ecosystem can stop treating x86 as the default assumption. Right now, the hardware is moving aggressively. Snapdragon X2 has pushed ARM deeper into premium PCs and desktops. NVIDIA is bringing an ARM-based CPU architecture into Windows machines aimed at workloads once considered safely inside x86 territory. Native application support is expanding year by year. Compatibility layers are becoming more capable because they still have to. That final detail is the clue. If ARM were irrelevant, Microsoft would not need Prism. If the ecosystem were already fully native, Prism would not matter. The emulator exists in the middle because the new hardware is arriving before every piece of old software is ready to meet it. Microsoft can port Windows. What it cannot port instantly is history, and ARM is now moving fast enough to make every year of that history visible.